All right, everyone, welcome back. In our last episode, we took a deep dive into the fascinating world of machine learning, focusing on support vector machines, or SVMs. We explored how these powerful algorithms came to prominence during the resurgence of AI between 1980 and 2010, right after the second AI winter.
We also talked about how the hype and eventual bust around expert systems paved the way for new developments, including the rise of SVMs. These mathematical tools revolutionized the way computers can identify patterns in data, helping us make sense of everything from spam filtering to medical diagnoses and even financial forecasting.
That's right. But today we're shifting gears to talk about something even more exciting, the revival and expansion of deep learning networks. We'll explore how deep learning has evolved, leading to the latest breakthroughs in AI, and how these networks are now powering some of the most impressive commercial applications. Get ready, because we're about to dive into the next chapter of AI's incredible journey.
And our guide for this journey is The Fourth Industrial Revolution and 100 Years of AI by Dr. Alok Agarwal. Really interesting stuff.
So, deep learning networks.
Well, it can get pretty complex, especially the idea that these networks can do amazing things, but we don't always understand exactly how. Kind of spooky, right?
A little bit. But first, let's start with the basics. Perceptrons, building blocks of deep learning.
Exactly. Think of them like artificial neurons trying to mimic how our brains work, like tiny computer brains. Each perceptron takes in a bunch of inputs, and each input has a certain weight assigned to it, so it adds up all those weighted inputs. If the total sum crosses a certain threshold, the perceptron fires a signal like, "Hey, I've got something," just like a neuron in our brain would.
So it's making a decision based on the strength of all those combined signals. That's cool. But are perceptrons really like our neurons?
They're inspired by neurons, but there are some key differences. Perceptrons mainly deal with signals such as zeros and ones, very digital. Our brains are more analog, with signals varying across a whole range.
Interesting. So it's a simplified model of how our brain works. But how do they actually learn? Like, how do those weights get adjusted?
That's where activation functions come in. These functions determine how a perceptron reacts to its input.
Okay, hold on. Back up a second. Activation functions?
Basically, it's not just an on-off switch. These functions introduce different ways for the perceptron to respond. It's like giving them different personalities. You've got tan, ReLU, sigmoid.
Sounds like a whole new level of complexity.
It is. Each function has its shape and its way of processing information. And all these different functions help deep learning networks tackle various tasks. Exactly. Like for probability problems, the sigmoid function is great because it squashes the output between 0 and 1. But for image recognition, ReLU is often more efficient.
So that's why we need all these different options. But doesn't this all tie into the black box issue?
Absolutely. When you have networks with tons of perceptrons, multiple layers, all these different activation functions, we can see the input and the output, but all those calculations happening in between, in the hidden layers, become really hard to interpret.
So we have these networks that can do amazing things, but we don't always know exactly how they're doing them.
Pretty much. It's powerful, but it also raises some big questions about trust and ethics. I mean, how much can we rely on a system if we don't fully understand its inner workings?
Right, that's a whole other discussion. But before we go there, let's step back and look at the history of all this. From what I recall, the term artificial neural networks appeared in 2000.
Yep. Even though the idea of perceptrons has already been around since the 1950s, and deep learning itself popped up as a term in '86.
Wow. And then between 1980 and 2010, things really started taking off.
Exactly. Researchers like Bengio, Hinton, Lacan, and many others really pushed the field forward. That's when we saw an explosion of different types of deep learning networks.
Yeah, there are 8 categories: fully connected networks, autoencoders, CNNs, so many more.
And each one has its own unique structure and purpose. We could do a whole separate conversation for each one.
Maybe we should. But for now, can you give us a quick example just to get a sense of how complex these networks can be?
Sure. Let's take convolutional neural networks, or CNNs. These guys are amazing at image recognition.
How so?
Imagine a network that can break down an image into smaller pieces analyze the features in each piece, and then put it all back together to figure out what the object is.
Wow, so it's almost like the network is seeing the image like our brains do.
Exactly. And that's just one example. Deep learning networks can have tons of hidden layers, each doing these complex calculations. I mean, a network can have 10 hidden layers.
10 layers. That's mind-blowing. Okay, so we've come a long way. We started with the perceptron, this artificial neuron.
With all those different activation functions, adding even more complexity.
Right? And all these perceptrons connect to form these incredible networks that can do amazing things, like recognizing images and understanding language.
But at the same time, it's a bit of a paradox. Deep learning is powerful because of its complexity, but that complexity also makes it hard to understand.
So we end up with these black boxes. Powerful, but mysterious.
Exactly. And that raises a whole bunch of questions about how much we can trust these systems and how we use them responsibly.
It's definitely something to think about. All right, let's go on a bit of a time travel adventure through the history of AI.
Sounds exciting. So we're not just talking about the latest trends?
Exactly. Some of the earliest breakthroughs might surprise you. Let's start with self-driving cars.
Wait, self-driving cars? How far back are we talking?
All the way back to 1977 in Japan. Tsukuba Mechanical unveiled a driverless car that could navigate by following white street markers, cruising at around 20 miles per hour.
Wow, that's decades before the tech boom.
Absolutely. Then in the 80s and 90s, Ernst Dickmans took it further with Mercedes vans outfitted with sensors and computers. One of his self-driving cars even hit 110 miles per hour on the Autobahn in 1995.
Impressive. But I bet they faced a lot of challenges back then.
Definitely. Navigating intersections and traffic with the limited tech of that time was tough. They were a bit ahead of their time, but they laid the groundwork for today's autonomous vehicles.
It just shows that progress isn't always a straight line. Okay, so what's next on our AI history tour?
Let's talk about handwriting recognition. Remember those old ATMs that struggled to read deposit slips?
Oh yeah, that was frustrating.
Well, that changed in 1989 thanks to Jan LeCun's convolutional neural networks, CNNs. These networks mimic how our brains see and were used to teach computers to read handwritten digits.
That's pretty cool. How long did it take to train the system back then?
It took about 3 days to train. And by the late 90s, NCR was using this tech to process 10% of all U.S. checks, and the Postal Service used similar systems to sort mail.
Amazing how that early tech evolved into things we use every day now.
Absolutely. And speaking of everyday use, let's dive into the evolution of speech and speaker recognition. Think of how we talk to our phones and smart speakers now. It all started decades ago.
It's hard to imagine life without those conveniences. This is just the start of how AI's history shaped what we take for granted today.
Exactly. But this tech has roots going way back. Remember Dragon, the early speech recognition system?
Oh yeah, the granddaddy of today's voice assistants.
That's right. In 1997, Dragon released Naturally Speaking 1.0. Fast forward to 2021, and Microsoft acquired it through Nuance.
Interesting. So, what else was happening in speech recognition during this time?
In the late 90s, deep learning networks were advancing in speaker recognition. These networks excel at learning from vast amounts of data.
Like our brains, learning from experience. Were they actually getting better at understanding us?
Absolutely. By 2007, they were using long short-term memory networks, LSTMs, which gave AI the ability to remember the context of speech.
So they could understand the flow of conversation, not just individual words?
Exactly. It made a huge difference in accuracy.
A big leap from the early systems that often misunderstood us.
Definitely. Now, ready for another blast from the past? Let's talk about recommender systems.
You mean those algorithms that suggest what to watch or buy next?
Exactly. They've been around longer than you might think. As early as 1990, Jesse Karlgren was working on digital bookshelves, the first recommender systems.
1990, before the internet really took off.
Yep, these systems work by collecting data about our preferences. There are two main approaches: collaborative filtering and content-based filtering.
Collaborative filtering groups users with similar tastes, right?
Exactly. If you like sci-fi and someone with similar taste recommends a movie, the system will suggest it to you.
And content-based filtering is more personalized.
Yes, it looks at your past choices, like a personal shopper who knows your style.
But how do they know what we like?
They collect both explicit data, like ratings, and implicit data, like watching habits, what you click on, how long you watch something, that kind of stuff.
Interesting. So they're always watching. Kind of creepy, but I guess it's for personalization.
Yeah. It raises some interesting questions about data privacy, but that's a topic for another conversation.
Absolutely. Now let's shift from the digital realm to something more physical, robots. This is where things start to feel truly futuristic. In 1994, researchers at Stanford University developed the CyberKnife, a groundbreaking surgical robot designed for tumor removal.
Cyberknife sounds intense.
It was. With incredible accuracy, it became a key tool in medicine, treating over 100,000 patients in the past 2 decades.
AI saving lives already, not just sci-fi anymore.
Exactly. And in 1997, NASA sent the Sojourner rover to Mars, a huge leap for robotic space exploration.
Amazing. What else was happening around that time?
Researchers were also working on robots that could interact socially. In 2000, we saw Kismet, a robot capable of recognizing and simulating emotions.
A robot with feelings? That's both impressive and unsettling.
Right? Then, there was Asimo by Honda, a humanoid robot that could walk and even serve trays at restaurants.
A robot waiter. Was it at least polite?
Still a bit early for robot etiquette. Okay, moving on. Remember Eliza, the early chatbot?
Yes, it mimicked conversation rather than understanding.
Exactly. But in the mid-90s, chatbots like Alice and Jabberwocky, later Cleverbot, got smarter, handling more complex conversations.
Still a work in progress, but better.
Right? And then came support vector machines, SVMs, which took off between 1995 and 1997.
SVMs? I've heard the term, but not sure what they are.
They're like the Swiss Army knives of machine learning, used for tasks like handwriting recognition, object detection, and face recognition.
Sounds versatile. They became widely used by 2010.
Exactly.
Interesting. From handwriting to faces, those SVMs really got around. Okay, what's next?
Let's talk about games. One iconic AI moment was Deep Blue defeating chess grandmaster Garry Kasparov in 1997.
That was huge.
It was. But Deep Blue relied more on processing power than advanced algorithms, analyzing 200 million moves per second.
So power over intelligence at that point.
Exactly. Still, it showed AI's potential to tackle human challenges. And AI made waves in other games too. In 1992, TD Gammon used reinforcement learning to master backgammon.
AI was taking over games across the board.
Yep. In 1997, Logistello, an Othello program, defeated the world champion. Early wins across the board. We've covered a lot: self-driving cars, robots, chatbots, but AI's impact goes far beyond games.
Like?
In 1996, AI was used to predict protein structure.
Protein structure? That sounds complex.
Proteins are like tiny machines in cells. Their 3D shape determines their function, which is crucial for drug development, therapies, and materials. In 1996, AI used statistical analysis to predict protein folding.
So AI built on existing knowledge rather than starting from scratch.
Exactly. This method evolved, with deep learning playing a big role in protein structure prediction today.
From microscopic proteins to space, where did AI go next?
AI helped analyze images from space telescopes like Hubble in the late 90s and early 2000s.
They trained algorithms to identify celestial objects?
Yep. AI sifted through vast amounts of data, leading to breakthroughs like discovering distant galaxies and mapping dark matter.
AI is helping us explore the universe. What about practical applications?
How about fraud detection? With the rise of online transactions in the late 90s and early 2000s, AI became crucial in spotting suspicious patterns.
It was a game changer, using machine learning to analyze transaction patterns.
Like an AI detective always on the lookout.
Exactly. These systems evolved with anomaly detection, predictive modeling, and network analysis, saving businesses and consumers tons of money.
Did AI also make waves in finance?
Absolutely. One major area was algorithmic trading.
Algorithmic trading? I've heard of it, but how does it actually work?
Imagine a super-fast trader making decisions 24/7 based on vast data and predefined rules.
So it's all done by computers?
Exactly. They execute trades faster and more efficiently than any human.
When did it take off?
It started in the 80s, but exploded in the late 90s and early 2000s as computing power grew and real-time market data became more accessible.
And AI played a part in this.
Yes, machine learning was incorporated to help systems learn from past market behavior.
So they adapt over time, not just follow rules?
Exactly. While it made markets more efficient, it also contributed to volatility. Think flash crashes.
A double-edged sword. What other industries felt AI's impact?
Customer service. Remember those frustrating automated phone systems?
Yes. Press 1 for this, press 2 for that.
AI-powered virtual assistants began emerging in the late 90s and early 2000s.
The ancestors of today's chatbots and voice assistants?
Exactly. Though still basic, handling simple queries and routing to humans when needed.
At least better than phone menus. So these systems evolved?
Yep. Now we have AI assistants everywhere. Websites, apps, and smart devices in our homes.
It's crazy how far we've come from those early days.
And this is just the beginning. So many exciting advancements ahead. Let's dive into a major breakthrough, ImageNet.
What's ImageNet?
A database with over 14 million images, each tagged with descriptions. It's like a visual encyclopedia for AI.
That's a lot of cat pictures, but why is it so important?
It revolutionized AI image recognition by providing a massive data set to train models on, overcoming the struggle of training AI on large data sets.
So it was like boot camp for AI.
Exactly. It launched in 2009. It quickly became the gold standard for evaluating computer vision algorithms.
So it sparked a ton of research and development.
Absolutely. It led to so many of the advancements we see today in image classification, object detection, all those things.
So ImageNet laid the groundwork for things like facial recognition on our phones, self-driving cars, medical imaging, all those cool AI-powered applications.
Exactly. Having access to that much high-quality data is a game changer for AI. Feed the AI, and it shall grow.
I like that. So what other big developments happened in this era?
Well, we have to talk about AlexNet.
AlexNet. Okay, what's so special about AlexNet?
There's this competition, the ImageNet Large-Scale Visual Recognition Challenge. It's where all the best image recognition algorithms go head-to-head.
So the AI Olympics.
Pretty much. And in 2012, AlexNet showed up and just blew everyone out of the water.
So it was like the Rocky of the AI world.
Exactly. Its accuracy was so much better than anything else. It really proved the power of deep learning for computer vision.
So we had ImageNet, the giant data set, and then AlexNet, the algorithm that used that data to achieve amazing results.
Right? Data and algorithms working together.
A powerful combination. And I bet AlexNet inspired a ton of new innovations in the field.
Oh yeah, it set a new standard. Everyone wanted to build the next best image recognition system, so we saw these convolutional neural networks evolve like crazy. VGGNet, GoogleNet, ResNet, all pushing the boundaries of what was possible.
It's like an AI arms race, but a good one.
And it wasn't just about images. This time also saw huge progress in natural language processing, or NLP.
NLP? That's all about how AI understands and uses language, right?
Exactly. Around 2013, a technique called word-to-vec emerged, and it changed how we represent words and their meanings in AI.
Word-to-vec? Sounds kind of sci-fi.
Maybe a little, but it's a really cool idea. Think of it as representing words as vectors, like coordinates on a map, but in a high-dimensional space. And the location of each word relative to the others captures its meaning.
So words with similar meanings would be close together, and words with opposite meanings would be far apart.
Exactly. It's like mapping the relationships between words.
That's pretty neat. But how did that actually improve things?
Well, it made AI systems much better at understanding language in general. Things like machine translation, sentiment analysis, question answering, even summarizing large amounts of text, and it paved the way for even more advanced language models. BERT, GPT-3, those can generate text that's almost indistinguishable from human writing.
It's amazing how far we've come. We've gone from simple chatbots to AI that can write poems, compose music, and even write code.
Right. And that leads us to another game-changing area, reinforcement learning. This is where AI agents learn through trial and error. They get rewarded for doing things right.
Reinforcement learning. I know about that. Like AlphaGo, the AI that beat the world champion at Go.
That's the one developed by DeepMind in 2016. It was a big moment for reinforcement learning. It showed AI could master incredibly complex games, things that require strategy and intuition.
Stuff we thought only humans could do. But reinforcement learning isn't just for games, right?
No way. It's being used in all sorts of fields: robotics, finance, and even healthcare.
Wow, it's like reinforcement learning gives AI a crash course on how to learn in the real world.
Exactly. It's a great way to develop AI that can handle all the messy, complex stuff of real life. This has been an incredible journey.
It really has. From those early self-driving cars to today's mind-blowing AI systems, it's amazing to see how much progress has been made and how much AI is already a part of our lives.
It's inspiring to see how far we've come. And it all started with those early pioneers who dared to imagine machines they could think of.
Makes you wonder what the future holds. What will AI be able to do in 10, 20, 50 years? What breakthroughs are just around the corner?
That's what's so exciting. We're only just getting started. But as AI continues to advance, we need to be thoughtful about its impact on society and make sure it benefits everyone.
Absolutely. The future of AI is in our hands. So to everyone listening, think about how you can contribute to its responsible development.
Exactly.
That wraps up today's conversation. Together, we explored how deep learning has evolved over time, leading to the latest breakthroughs in AI, and how these networks are now powering some of the most impressive commercial applications in fields like healthcare, space exploration, and finance.
Exactly. And there's so much more to explore in AI's evolution. In our next episode, we'll take a closer look at the period between 2011 and 2023, a time when AI truly started to rival humans in key domains. You'll dive into the rise and fall of IBM Watson, the stunning progress in deep learning networks, and the emergence of generative adversarial networks and diffusion models. We'll also explore the spectacular rise of transformers, some of the most powerful AI systems to date. Plus, we'll look at the key domains where AI systems have really made strides, from language processing to image generation and beyond. It's going to be an exciting episode, so be sure to tune in. Thanks for listening, and we'll catch you next time on our AI journey. See you then.